This will be a second example for electric flux, this time using a closed surface. So the surface that we'll use this time will be a cube. So imagine that this actually looks like a cube. This cube has sides of length L and has an electric field passing through it. This electric field is uniform. And it is perpendicular to the left and right sides of the cube. Go ahead and label that. So what we're interested in is what is the total electric flux through the cube. So let's tackle the easy parts first. We'll go surface by surface, so side of the cube, one side of the cube at a time. So we'll start with the top of the cube. Now, the problem statement said that the electric field is perpendicular to the left and right sides of the cube, which is going to make it parallel to all the other sides. So it's going to be parallel to the surface of the top side of the cube. If it's parallel to the surface, that automatically means that our electric flux through the top surface, top side of the cube, is 0. Since it's also parallel to the bottom of the cube, the front of the cube, and the back of the cube, we can also automatically write So we're left with the right and left sides of the cube to deal with. Moving on to the left side of the cube, here we know that the electric field is perpendicular to the surface of the cube. So in shorthand, the electric field is perpendicular to the surface. So if we calculate the electric flux for the left side of the cube, it's going to be equal to the electric field times the area of the surface times the cosine of the angle between them. Since it's perpendicular, that cosine theta is equal to 1. And we have electric field equal to the area. The area of a square is the length squared. So we end up with EL squared. Now for the right side of the cube. Very similar procedure. The electric field is also perpendicular to the surface of the right side of the cube. So the electric flux through here is, that should be right. Same as we had with the left side. That cosine theta goes to 1. Electric field times the area is equal to the electric field times the length squared. So now to determine the total flux through the cube, we need to sum all of the individual fluxes. Most of those were 0, so I'm going to go ahead and leave those out. So we're basically just left with the left and the right. When we calculated them previously, we did not include any sign designation to denote what direction the flux was going, whether it was going into the box or out of the box. So let's go ahead and make into the box correspond to positive flux. So that means now when we look at our total flux, we're going to have the flux through the left side of the cube. If we go back to our diagram, the electric field is pointing into the box on the left side. So that's going to be EL squared. And then on the right side of the box, it's going out. So that's going to be negative EL squared. You'll see that these two cancel, and we end up with 0. So, for a uniform electric field, a closed surface, and no charges inside, which at this point we don't have any separate charges, we know that the electric flux is 0.